Hi everyone. So in today's session, we are going to continue with the fluid mechanics, the first module, the properties of fluids. So in that, let's start with the continuation of after discussing the primary properties, then how the types of fluids has been classified. So here the types of fluids. So ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, ideal plastic fluid. So before that, so what all we have discussed in the primary properties and the secondary properties of fluids. So when it belongs to the secondary property, what we have discussed about the viscosity, based on this, it has been classified. So what are all the types of fluid? It is based according to the Newton's law of viscosity. So we know that viscosity is nothing but the shear stress is directly proportional to shear strain. But how the shear stress is being developed? So to know that, what you are having the fluid which is having two layers, the two layers causes the friction. That friction is nothing but there is a stress. That type of stress is shear stress. So when the shear stress is directly proportional to shear strain, we will call that will be as viscosity. So according to Newton's law of viscosity, so Newton says that the shear stress is directly proportional to shear strain. So here we can see the types of fluids. So when it is coming to the types of fluids, ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, ideal plastic fluid. And here it is in terms of graphical representation also. Here the tau represents the shear stress, and here du by dy represents the velocity gradient, or what we can say shear strain. So the first one, the types of fluids according to Newton, ideal fluid. So ideal, in the name only it's ideal. Ideal is nothing but when it is at rest, or what I can say, it is just an imagination. Ideal fluid is a type of fluid, but the fluid which is only there in imagination. It is nothing but which doesn't possess a viscosity, and the fluid is incompressible. So the fluid which is incompressible and doesn't have viscosity, will say that will be as ideal fluid. Then the second one is real fluid. So the real fluid, real is nothing but the fluids which are all there in the practices. So whether it is shear stress is directly proportional to shear strain, or it is indirectly proportional, but the fluid which are all there in the practices, so we'll say that will be as real fluid. Then Newtonian fluid. So according to Newton, what is fluid? It is nothing but, again Newton says it is with respect to the viscosity concept. So when with respect to the viscosity concept, the shear stress is directly proportional to shear strain. Then non-Newtonian fluid. So it is nothing but doesn't obey the Newton's law of viscosity. In non-Newtonian fluid, it is a fluid which is having the shear stress is not directly proportional to shear strain. Then ideal plastic fluid. So here in ideal plastic fluid, the shear stress is directly proportional to shear strain, but the shear stress value is more than the yield value. So when the shear stress is having more than the yield value, then after that shear stress is directly proportional to shear strain. So we'll say that will be as ideal plastic fluid. So what I explain now, the classification of fluid according to Newton, that will be expressed in terms of graphical representation. So here in the y-axis, it is about the shear stress. In the x-axis, it is about the shear strain. So we can see here, when it is coming to the ideal fluid, it is imagination fluid which is incompressible and which doesn't obey the viscosity. So it is nothing but it will be in zero line. So that's why it is ideal fluid. It may be in x-axis or it may be in y-axis, but it will be at zero equation. The next is real fluid. So real fluid, all the fluids which are all there in the practice, which are all there as a real, we'll say that will be as a real fluid. Okay, means which has to be having the properties, which has to obey the viscosity. Then Newtonian fluid, we can see here from zero, it is a straight line. It is nothing but the shear stress is directly proportional to shear strain. You'll get a straight line that indicates what you are having this. The shear stress is directly proportional to shear strain. How much it has been increased, that much only it has to be increased in shear strain. The shear stress is directly proportional to shear strain, then only this will be a straight line. This is Newtonian fluid. The non-Newtonian fluid, which doesn't obey the Newton's law of viscosity. It is nothing but the shear stress is not directly proportional to shear strain. We can see here a curved line that indicates it is non-Newtonian fluid. And ideal plastic fluid, the shear stress is directly proportional to shear strain, but which is having more than the yield value. So the shear stress, it is not from the origin, it is having some value. After that, from this point will be considered as origin. From here, the shear stress is directly proportional to shear strain, but it is not from the 0th point. The shear stress is having more than the yield value. After this point, then only the shear stress is directly proportional to shear strain. This is about ideal plastic fluid. So these are all the types of fluids with respect to Newton law of viscosity. Then next, with the numericals, you can see here, if the velocity distribution over a plate u is equal to 2 by 3 y minus y square, in which y is equal to 0 and y is equal to 0.15 meter, assume viscosity as 8.63 poise. So in this question we can see that the velocity distribution over a plate, it is nothing but what is the velocity of the plate and how it is moving in terms of parabolic equation, that is u is equal to 2 by 3 y minus y square, and y, what is y? Y is nothing but the thickness of the fluid. So the thickness of the fluid will be given, there are two conditions. One, y is equal to 0. The first condition says that the thickness of the fluid is 0. Then the second condition says that the thickness of the fluid is 0.15 meters. And we have to assume the viscosity, that is mu, as 8.63 poise. But we should express in terms of Newton second per meter square, SI unit. So 8.63 poise is the CGS unit, that should be converted in terms of SI units. So 1 poise will be equal to 1/10 of Newton second per meter square. So before doing the solution, just write down the given data. Given data is the velocity of the plate is u is equal to 2 by 3 y minus y square, and y is equal to 0 and y is equal to 0.15. Assume the viscosity, mu is given as 8.63 poise. So we know that 1 poise is equal to 1/10 of Newton second per meter square. Then mu is equal to 8.63 by 10, that is 0.863 Newton second per meter square. And we should remember here what we have to find out. So we have to find out if the velocity distribution is u is equal to 2 by 3 y minus y square for these two conditions. When y is equal to 0 and when y is equal to 0.15, what will be the shear stress? So to find out that, we have only this one, in terms of u, but we need in terms of tau is equal to mu into du by dy. Mu is given, we have to find out what is the tau shear stress, but du by dy is not given. But we have the equation in terms of u, in terms of y. So if you differentiate u with respect to y, then you will get the equation. That is, u will become differentiation of u with respect to y, then you will get du by dy will be as 2 by 3 minus 2y. Okay, so once you differentiate u with respect to y, then you will get du by dy is 2 by 3 minus 2y. Then du by dy when y is equal to 0, substitute the values, 2 by 3 minus 2 into y is 0. Then you get 0.667 per second. So what you are having, du is meter per second, dy is meter get cancelled, you will get per second. So the SI unit for velocity gradient is per second. Then du by dy when y is equal to 0.15 meter, then that will be 2 by 3 minus 2 into 0.15. Then you will get 0.367 per second. So we are getting to know from both the conditions, that is when y is 0 and when y is 0.15. That is 0.667 per second and 0.367 per second. But what you have find out now, it is in terms of du by dy and du by dy. But the condition is we have to find out what is the shear stress when y is at 0 and when y is at 0.15. So mu is given, that is 8.63 poise, that will become 0.863 Newton second per meter square, and du by dy in terms of SI unit per second, then we can substitute and we can find out. That is, here we can see first condition when y is equal to 0, when y is equal to 0 at shear stress, mu into du by dy, mu is 0.863, then into 0 du by dy when y is at 0 is 0.667, then here it is Newton second per meter square, here it is per second. Both the second will get cancelled, then it is Newton per meter square. We have to remember stress is force by area, then the unit should be Newton per meter square. Again here also we will get the same Newton per meter square, because here it is Newton second per meter square into per second, then second shift will get cancelled, you'll get only Newton per meter square. Then shear stress is 0.5756 Newton per meter square when y is at 0 meter. In the second one, when the shear stress which is having y value is 0.15 meter, then tau is equal to mu into du by dy, then tau when y value is at 0.15, that is 0.863 is mu, then du by dy when y is at 0.15, that is 0.367, then the shear stress at y is equal to 0.15 meter will be 0.3167 Newton per meter square. So these are all the way to solve the numericals when they ask in terms of viscosity concept with in properties of fluids. Thank you.